Draw the shear and moment diagrams for the beam, indicate values at the supports and at the points where a change in load occurs. To begin, first of all, we need to convert our distributed load into a point load. This will become 20K. And then we have our external reaction forces at A. AX is going to be 0 because of no other horizontal force present on this beam. And then AY is simply going to be positive 20K because we have negative 20K alone as another vertical load. And now to find our moment at A, we just need to take moment above the point A. So we're going to have positive moment A, positive 20 times 5, and then clockwise 30 moment on the other side. Solving for moment A, we get our solution as negative 70 pound-foot. And now we can start drawing our shear diagram. Or so we're going to begin at 0, and then our shear goes all the way till the end, and it ends at negative 20. And then at point A, we get positive 20, and this gets our moment back to 0, and this means we did our calculations correctly. Now we can draw our moment diagram. So for our moment diagram, we're going to start at 30, and then we have this area, which is going to be half times negative 20 times 10, comes up to be 100. So 30 take away 100 is 70, so we're going to go down till negative 70. And this curve is going to be second order, and this is first order, by the way. We're just going to, I'm going to redraw it so that it looks a little bit better. Something like this. And then at 70, we have moment A, which takes our moment curve back to 0 and also clarifies that the calculation we did was correct. And before we finishing this problem, we have to find our point of intersection for this curve. And to find that, we know that our load equation is simply going to be negative 20. And our shear equation, which is basically integral of the load equation, going to be 2x and then 2 for our load, and then plus c, which is a constant, but we know our diagram starts from 0, so c is 0 in this case. And then our moment equation is simply going to be negative x squared plus c. C in this case is positive 30. So to find our point of intersection, we can have our moment at 0, and then we basically search for x squared, which is going to be square root of 30. Square root of 30 is 5.477, and that's our draw the shear and moment diagrams for the beam, indicate values at the supports and at the points where a change in load occurs. To begin, just like previous example, we're going to have to find our point load first of all. And our point load is going to be 6 times 12, which is 72K. Now we can find our external reaction forces. Our AX is going to be 0. AY and BY we need to determine. Now we can take a moment about the point B to find our solution for AY. We're going to have 18 times 12, and then 72 times 18, and then negative AY times 24, all equals to 0. All for AY, we get our solution as 63. Now we can basically sum the forces in y direction to find our solution for BY. We're going to have BY as 27K. Now we can start drawing the shear diagram. So our shear diagram is going to look something like this, where it starts at positive 63. And then 63 take away 72 is 9. So it's going to go all the way till negative 9. And then negative 9, we're going to have shear from the external load of 18. I'm going to get down to negative 27. From negative 27, it just flatlines all the way till point B, where we're going to have 27 and going to get us to 0. And also confirms that our calculation was correct. But before we move over to our moment diagram, we need to determine our point of intersection here. To do that, we need to find our equations. So we know that we'll need to divide this beam into two segments. One will be 0 to 12 and the other one will be 12 to 24. For this first region, we know that our load equation is going to be simply negative 6. Then our shear equation is going to be negative 6x plus c, and our c is 63 in this case. And then we have our moment, which is going to be negative 3x squared plus 63x plus the constant, which we'll solve later, but it's good enough for now. Now we can use our shear equation to determine our point of intersection. So it's just simply going to be shear, where shear is 0. We're going to have 63 divided by 6 goes to x and becomes our point of intersection is 10.5. Now we can draw our moment diagram. Our moment diagram starts at 0 till 10.5. We're going to have to use this area, which is basically 0.5 times 63 times 10.5. And we get our value to be 330.75. And it's going to be second order curve. Then at 12, you're going to have this area, first of all, which is 0.5 times 9 times 1.5. Negative, and that means our value here is going to be 324. After that, we just have this rectangular area, and it's negative. We're gonna have negative 27 times 12, which is negative 324, and this curve is going to be first order, and also gets it to 0, confirming that our equation was correct. We can stop here, or we can determine our constant value, which we didn't do it earlier. We don't really need it for this problem, but we're gonna do it anyways. So we know that when our moment is 0, our x is 24. Pardon me, that's for the second phase and not for the first. For first, it's our constant is simply going to be 0 because we start at 0, so just 3x squared plus 63x. But for our second half, we know that our weight equation is 0. Our shear equation is simply negative 27, and from that our moment equation is going to be negative 27x plus c, our constant. And in this case, we know that when our moment is 0, our x is 24. And solving for c, we get a solution as 648.